Section: Introduction. In this section, we explore how language models, LLMs, process text and convert groups of subword tokens into meaningful representations, a process known as detokenization. LLMs work with a set vocabulary of tokens, where each token can represent a single word or a part of a word. However, the tokenization process can sometimes lead to unintuitive results, such as breaking down words like northeastern into unrelated subword tokens. Despite these challenges, large LLMs seem to handle these tokenizations well during training without affecting their performance significantly. We believe that during training, LLMs develop a hidden vocabulary that maps groups of tokens to meaningful units like multi-token words or named entities. These units are non-compositional, meaning their meanings cannot be predicted from individual tokens. To understand how LLMs manage these tokenizations, we investigate how information is stored at the token level in LLM representations. We observe that the last token positions of multi-token words and named entities play a crucial role in erasing token-level information in the early layers of LLMs. This erasure effect indicates a mechanism in the early layers that helps form meaningful lexical items. Previous studies have shown that information about multi-token entities is often concentrated in the last token of that entity. This phenomenon may be due to the nature of decoder-transformer models, where information enrichment about an entity occurs at its last token in the early layers. Other research has also found evidence of LLMs encoding lexical items in their representations. To further investigate the importance of last token positions, we examine hidden states in LLMs to see if they encode information about other subject tokens. We train linear probes to predict nearby tokens based on hidden states at different layers and token positions. By analyzing these hidden states, we aim to understand how LLMs store and process information about tokens in their representations. Section Summary. In this section, we explore how large language models, LLMs, process text by investigating the mechanisms behind converting groups of subword tokens into meaningful representations, a process known as detokenization. We propose that during pre-training, LLMs develop an implicit vocabulary that maps arbitrary tokens to semantically meaningful units, such as multi-token words or named entities. By analyzing token-level information stored in LLM representations, we find that the last token positions of multi-token words and named entities play a crucial role in erasing token-level information in early layers, indicating a mechanism that orchestrates the formation of meaningful lexical items. Section: COUNTERFACT subjects. In this section, we trained probes and then tested them on the COUNTERFACT dataset. This dataset contains prompts related to subjects that require factual knowledge to answer correctly, such as, Mount Passil is in Antarctica. We filtered the dataset to only include prompts that our model answered correctly. This filtering resulted in 5,063 examples for Llama 2 to 7b and 5,495 examples for Llama 3 to 8b. To expand this dataset, we also included album, movie, series Writero creator pairs from Wikidata, resulting in a total of 12,135 correctly answered prompts for Llama 2 to 7b and 13,995 for Llama 3 to 8b. When we tested the probes on the COUNTERFACT dataset, we noticed an interesting phenomenon. The hidden states of the last tokens of COUNTERFACT subjects consistently forgot about the preceding and current tokens, which we refer to as an erasure effect. However, subject tokens that were not in the last position did not show this pattern. This drop in token accuracy is similar to what happens during the subject enrichment stage, indicating that certain tokens may be overwritten in the process of representing concepts like Star Wars. We also observed a similar phenomenon when testing on named entities identified by Spacey in Wikipedia articles, suggesting that this effect is not specific to the COUNTERFACT dataset. Furthermore, we investigated whether this result was due to imbalances in the probe training data but found that this was not the case. Moving on to multi-token words, we found that the process of converting sequences like _n, ort, he, estern, into northeastern is akin to converting _e, iff, l, tower, into Eiffel Tower. Models seem to treat multi-token words similarly to multi-token entities, as we observed the same erasing pattern for both. This implies that they may be processed in a similar manner in the early layers. After examining the behavior of probes for multi-token words and entities, we theorized that the erasure effect stems from the implicit formation of lexical representations in the early layers of the model. To further understand this phenomenon, we introduced an erasure score, psi, to identify token sequences exhibiting the observed pattern. This score helps us identify implicit vocabulary entries in the model. The erasure score, psi_p, q, quantifies the erasing behavior at token positions within a sequence and penalizes any erasure of tokens outside of these boundaries. It is designed to capture the drop-in probability of predicted tokens from layer 1 to layer L. We explain the intuition behind this approach in more detail in the appendix. We developed an algorithm based on the erasure score to segment documents into high-scoring, non-overlapping sequences. This algorithm breaks down a given document into segments that cover the entire document based on their erasure scores. The top-scoring sequences represent plausible non-compositional lexical items. Examples of complete segmentations can be found in the appendix. Section Summary. In this section, we test our probes on the COUNTERFACT dataset, focusing on subjects that require factual knowledge to answer correctly. By filtering the dataset to include only prompts that the model answers accurately, we obtain examples for our models. We observe a significant erasure effect for the last tokens of COUNTERFACT subjects, indicating a potential overriding of certain tokens in the representation process. Section: Model Vocabularies. In this section, we introduce a method to uncover the hidden vocabulary of a model M, using a dataset D. We divide each document D in D, using a specific algorithm. Then, we calculate average scores psi for all multi-word sequences that appear more than once across all documents. Since this process relies heavily on the data, we compare the top 50 outcomes for Pile and Wikipedia text in the appendix. By applying this method, we identify around 1,800 sequences for Llama 2 to 7b and about 900 for Llama 3 to 8b using the same set of 500 Wikipedia articles. Although the recall rate is relatively low, refer to the table, we discover that almost 45% of the sequences found for Llama 2 to 7b in Wikipedia text are either multi-word terms or multi-word entities, approximately 30% for Pile text. For Llama 3 to 8b, only 5% and 3% of the sequences are multi-word terms or entities. However, when examining examples of Llama 3 to 8b sequences in the appendix, we notice other interesting cases, such as multi-word expressions, gold medalists, by per capita income, thank you for your understanding, and latex commands, as also noted by. Since Llama 3 to 8b has a token vocabulary 4 times larger than Llama 2 to 7b, its implicit vocabulary appears to include more multi-word expressions and code segments rather than multi-word terms. Refer to the appendix, table.